All right, let's begin. So, um, our topic for today will be angle chasing, and yeah, just enjoy. First of all, what is angle chasing? Angle chasing is basically using the using the relationships between the angles to determine more information about unknown angles and angles that we want to find more information about. All right, let's first review. So the first two slides will most likely be review about information taught in a high school geometry course. So we're not going into too much detail. It'll most likely be review. So our first topic is parallel lines. So in parallel lines, the corresponding angles are congruent, the alternate angles are congruent, and the same side interior and exterior angles are supplementary. So for example, in this figure, we have that EGB and GHD are corresponding angles, which means that they are congruent. Sorry. And similarly, EGB and CHF are congruent since they're exterior alternate angles. And for our third point, we have that HGB and AGE. Sorry, HGB and GHD are supplementary since they're same side interior angles. Let's go to an example. So we have this diagram to the right, and based on our last slide, we can make some claims. So my first claim is that we have EGB is congruent to angle GHD simply because those two angles are corresponding angles, which is then equal to angle CHF. Why? Well, angle GHD and CHF are vertical angles, which means, they're congruent. And then which is then equal to angle AGH. Why? Well, angle CHF and angle AGH are corresponding angles. So all of these four angles are congruent. And then in a similar fashion, we can show that the other four angles are congruent as well. So for example, we have that AGE is equal to angle CHG, which is then equal to angle FHD, and that is equal to angle HGB, simply because all those angles are either corresponding angles, alternate angles, or vertical angles, which means that they're all congruent. And then we can also notice that all the angles in the first bullet are supplementary to the angles in the second bullet, simply because they're either add up to 180, or like they're on a straight line. So for example, angle AGE is equal to angle EGB because angle AGB is a straight line, right? Or they're same side angles, which means that they are supplementary. Right? If anyone has any questions, just feel free to ask. Just type it in the chat, and then I'll answer it. Okay, so here are some other facts about triangles and other figures that frequently occur in angle chasing. The first one is just a triangle sum. So the angles in a triangle sum to 180 degrees. The second one is just a definition of an isosceles triangle. So if a triangle is isosceles, the base angles are congruent. And the third fact is just the sum of the angles in a quadrilateral. So the angles in a quadrilateral sum to 180 degrees. 360 degrees. And of course, this can be generalized to any n-gon. So for a 3-gon to the triangle, this angle is summed to 180 degrees. In a 4-gon, the angle is summed to 360 degrees. And of course, this keeps on going. All right, so let's move on to our next topic, which is about circles. the central angle is equal to the measure of the arc it cuts off. So in our first diagram, for instance, the measure of angle CAB equals the measure of minor arc CB, right? Because A is the center. A is the center of a circle, and so it means it's a central. It's a central angle, and arc CB is the arc it cuts off. And in the second figure, so if we have a diagram like this again, um, D is the center of a circle, but that shouldn't be that's irrelevant. So if we have an inscribed angle, then its measure is equal to half the measure of the arc it cuts off. So So for example, in this figure, we have that angle GFE is equal to half the measure of arc GE. Right? See that? So this is the inscribed angle, and this is the arc. And F obviously lies on the circle. So now I'd like to present two more configurations. So we have a figure of something like this, then the measure of angle, if we have the measure of LMI is equal to the measure of arc LI subtracted by the measure of arc QR divided by 2, right? So if we have two secants that intersect, and their intersection is equal to the larger, smaller arc subtracted from the larger arc divided by 2, right? And in the second configuration, we have two chords. Then the measure of the intersection of two chords is equal to the average of the two arcs. So for example, in this figure, the measure of angle OSP equals the average of arc OP and NK, right? And also notice that OSP and NSK are vertical angles, so they're congruent, obviously. So that means these two, both OSP and NSK are equals to the average of angles of arcs OP and NK. So we have a question. So configuration 1 is like configuration 2, but the convex arc QR becomes negative. I guess you could think about it like that. Yeah, that's true. Yeah, I guess you could think about it. Yeah, that makes sense. Yeah, I think we use a pointer. Okay. Right. Yeah, now you should use my cursor. Nice. Okay. So notice in both configurations, the center is irrelevant, right? So although we have the center marked H and we have these segments, we have segment HL and HI, it don't really matter, right? Since we just care about arcs QR and LI. And in this figure, the center J is just by itself. So yeah, we don't even use J. So now I would like to present a theorem. So theorem 1, all the inscribed angles in this of the same arc in a given circle are congruent. So for example, in this figure, angle UWV is equal to angle UZV, right? You can read the proof, but I'll give a summary of it. So basically, just notice that both of these angles, UWV and UZV, are half the measure of arc UV, right? So since they're both half the measure of arc UV, then they must be the same, right? So this is true if we have if for any inscribed angle. So UV, so W is just a point on the circle. So if we just move W like here or something, it'll be the same. It'll always be half the measure of arc UV. So everything will be equal. Alright, so our next topic will be tangency. So the theorem, the angle created by a tangent line and a secant through the point of tangency is half the measure of the arc it cuts off. So if we use this figure on the right, we have tangent line DB, and we have the secant CB. Notice that B is the point of tangency with the circle C. So basically what this theorem is saying is that angle CBD is half the measure of arc CB, right? Since the angle created, this is the tangent line, and this is the secant, and this is the angle created by those two lines, and this is the arc it cuts off, right? CB is the arc. Oh, sorry, I think so that's the question. What if the point resides on the minor arc? For which slide do you mean? Oh, never mind. He sees it. Okay. Yeah. So we won't try to prove this yourself. We won't prove this on stream. If you want, you can discuss it in our Discord server, which is on our website. And yeah, if you type it there, then our staff will be able to check it for you, see if it's correct. You can also discuss it with other people. So, an intuitive way to realize this and to like think about it, well, it's also the way I think about it, is that let DB be a secant, but both of its intersections occur at B. So B are both the intersections of this line with the circle. So basically, the intersections are infinitely close together, right? And then you can just apply the previous theorems of you just apply some theorem. I don't know, but like basically, yeah, that actually worked. Before we move on to our a new topic, which is like probably the most important topic in angle chasing, does anyone have any questions? Okay, if there aren't, we'll move on. So this is probably something new, and it's one of the most crucial ideas in angle chasing, which is cyclic quadrilaterals. And a definition of basically what it is that it's basically a quadrilateral that can be inscribed within a circle. So in this figure to the right, we have that quadrilateral HGFI is inscribed within this circle D. So that means quadrilateral HGFI is a cyclic quadrilateral. And there are usually two main ways to determine if a quadrilateral is cyclic. The first one is if the opposite angles add up to 180 degrees, which means that the opposite angles are supplementary. So for example, in this figure, since we know that HGFI is cyclic, angles HGF and angles HIF add up to 180 degrees, and that means they're cyclic. They're supplementary. Similarly, we can also say that angles GHI and GFI are supplementary, and they add up to 180 degrees. And the other way to determine if a quadrilateral is cyclic is if the angle between a diagonal and a side is equal to the angle between the other side and other diagonal. For example, we have in this figure that angle HGI is equal to angle HFI, right? Since we have these two main diagonals and these two sides. And also notice that they both cut off arc HI, but they're both half the measure of arc HI, right? So that also means that they are congruent. A big thing about cyclic quadrilaterals is that the properties can be used both ways. So if a quadrilateral is cyclic, then we can use both of these properties. So we know that the HGFI are cyclic, so we can use both of these properties, right? The other thing is that if we know that if either one of these properties is true, then we know the quadrilateral is cyclic, and then we can use the other fact, right? So if we aren't given that it's cyclic, and we are just given that angle HGI is equal to angle HFI, then we immediately know that quadrilateral HGFI is cyclic, and then we use the other fact, right? Okay. Basically, these two, they can be used in both directions. Both properties can be used in both directions. Are there any questions? Okay, I'll move on. Okay, so now we'll begin our sample problems. We'll have 3 of them, and they'll be an increasing difficulty. So I'll give you like maybe 1 or 2 minutes to read the problem. Here's a diagram, and though this is the solution, so if you want to give it, if you want to try it yourself, just don't read that part. And just think about it. It could be like maybe a minute or so. One second, we're having some technical difficulties, so 1 second. Okay, so let's discuss the solution.
Okay, so we have that L is the center of the circle, and um, we have a line tangent to the circle at M. So at this point O, so line OM is tangent to the circle. We also have a line RQ that is parallel to the line tangent at M. And notice that, we have this diagram, and the line RQ goes through point L. We're also given that if that angle OMN is equal to OMN is equal to 50 degrees. And we're asked to find the measure of minor arc PQ. And just so just to like get FYI, minor arc means that means a shorter arc. So minor arc PQ would be this arc right here. Okay, so from the first bullet, we can okay, okay. So first of all, from a property of a tangent line, is that if you draw the radius from the point of tangency, then the tangent line is perpendicular to the radius. So in this figure, we have that line MO is perpendicular to line LM, right? And we're also given that line RQ is parallel to line MO. This means that angle MLR is right. Since we have that this angle is right, this angle must be right as well. So, since also notice that angle RLM is an inscribed angle, is a central angle. Sorry, is a central angle. So arc RM is 90 degrees as well. And also, we are also given that angle OMN is equal to 50 degrees. But this is also equal to angle LNM. Why? Well, they're alternate interior angles. Since remember that RQ is parallel to MO. But remember from one of our previous properties, angle LNM is half the sum of arc PQ and RM. In other words, it's the average of arc PQ and RM. So since we know that arc RM is equal to 90 degrees and angle LNM is equal to 50 degrees, we create the equation half of arc PQ plus 90 degrees is equal to 50 degrees, right? Since we know that RM is 90 degrees and angle LNM is 50 degrees, so we need to substitute the information into this equation. And we just have a basic equation that we can solve. And if you solve this, you get that arc PQ is equal to 10 degrees. So for a sketch of how we solve this, we just multiply both sides by 2 and then subtract 90 from both sides. We just get arc PQ is equal to 10 degrees. Okay, any questions? Before we move on. Okay, let's move on. So I'll give you like 2 minutes or so to read the problem. And yeah, here's the diagram that I created. I also drew in some extra lines to save some time. But yeah, I'll read like 2 minutes to read the problem and think about it. Okay, now that it's been a few minutes, let's talk about it. Alright, so I'll probably not have space to do it here, so I've created something else. And let's, okay, so it's the same problem. So we have that ABC is an isosceles triangle, and AB with AB equals AC. And gamma is a circumcircle. So I've labeled that as well. A point D is on arc AB of gamma not containing C, so it's over here somewhere. And a point E is on arc AC of gamma not containing B, so it's on minor arc AC somewhere. We are also given that AD equals CE. And we're trying to prove that BE is parallel to AD. So I've also drawn some extra lines to save time. I think I already mentioned that. But yeah. So immediately looking at the diagram, we somehow want to use one of our properties of parallel lines to prove that BE is parallel to AD. Right? So one of the two ways to do this is to show that angle DAB is equal to angle ABE, right? Since they're alternate interior angles. And once we can do that, then basically tells us that DA is parallel to BE, which is what we're trying to demonstrate. So let's first begin by doing some angle chasing, which is, well, or just talk about the lecture. Right, okay. So the first thing I notice is that we have three angles that cut off arc EC, right? So we have that angle EBC is equal to angle EDC, which is then equal to angle EAC. However, we are also given that AD is equal to CE. So arc DA is equal to arc CE, which means that angle AED is then congruent to all these angles as well, right? So notice that angle EAC cuts off arc EC. Since arc EC is equal to arc DA, then these two angle EAC must be equal to angle AED, right? So that's why all these four angles are congruent. But also notice that angle APE is equal to angle DPC, since they're just vertical angles. Then by angle, triangle EAP is similar to triangle DCP. And notice that since triangle AEP is isosceles, since these two angles since angle EAC is equal to angle PEA, these two angles are, so they're isosceles. Now this means that triangle DPC is isosceles. So this angle is congruent to them as well. Now remember that we are also given that ABC is an isosceles triangle. So this means that angle, actually let me write this down, that angle ABC equals angle ACB, right? Since that's just a property of isosceles triangles, of an isosceles triangle. So this means that angle ABE must then be equal to angle DCB. Why? Well, we have the angle ABC equals to the angle ACB, and when both of them we subtract the measure of EBC, right? Since we both subtract the angle with one line, whatever you want to call this thing, right? So this means that we have these two angles that are congruent. And that's nice. Since now we notice that DCB, it cuts off arc DB, right? So this is really nice because now we can see what angle also cuts off arc DB. This, well, that another angle is angle DAB, right? Since DA and AB, yeah, it cuts off arc DB. So this means that angle DCB is equal to angle DAB. We can mark that in the diagram. But this is our goal. So what we wanted to show. We wanted to show that the angle DAB was equal to angle ABE, right? Because that implies that DE is parallel to AD. But now we're done. Since we've shown that angle DAB is equal to angle ABE. So this proves that BE is parallel to AD. Okay, we have one more example problem. And this is from the 2020 USOJMO. And again, I'll give you a few moments to think about it. Okay, now it's been a few minutes. So let's come back to the problem. Again, okay, it's here. All right. So we are given that ABCD is a convex quadrilateral inscribed in the circle, and DA is less than AB, which is equal to BC, which is less than CD. So immediately from our first sentence, I can deduce that quadrilateral ABCD is cyclic, since we're given that it's inscribed in a circle. And then, so we also have these other lines. So AD is less than AB, which is equal to BC, less than CD, which is drawn in the diagram. And also, in our second sentence, we're given that E and F are chosen on sides CD and AB, such that BE is perpendicular to AC, and EF is parallel to BC. So not really immediately, but we're given. Let's start with point E. So we're given that it's either on CD or AB, and also given that BE is perpendicular to AC. So immediately, it's easy to see that E cannot lie on AB. Otherwise, its intersection point with AC would be at A, and hence it could never be never be perpendicular with AC. This means that E must lie on CD. And in a similar fashion, we're given that F lies on either CD or AB. And we're also given that EF is parallel to BC. However, if F lied on CD, then there is no way it would be parallel to BC. So F has to lie on line AB in order for it to be parallel, in order for line EF to be parallel to BC. So now we've constructed our diagram, and we can make some decorations in order to make it easier for us to work with the problem. So EF, BE is parallel to AC, and we're given that F is parallel, right? So first notice that the problem asks us to prove that FB is equal to FD. Now, since we're given lots of angle relationships, they're given parallel lines and perpendicular lines and cyclic quadrilaterals, it'd be quite difficult to work with lengths. So we try to change this into working with angles. And also the topic of this lecture is angle chasing, so there's no point. Though I wouldn't choose a problem that'd be length chasing. That'd be quite dumb. So we construct triangle FDB, and rather than directly prove that FB is equal to FD, we can change this into proving that angle FDB is equal to angle FBD, since this means that triangle FDB would be isosceles, and hence meaning that FD would be equal to FB. So we can write our goal as to show that angle FBD is equal to angle FBB, right? So this is our goal. And if we can show this, then we show that FB is equal to FD. Also, okay, so the first point is to notice that ABCD is cyclic as given. So also notice that FE is parallel to BC, which means that angle ABC is equal to angle AFE. So let's write that down. Right. But also remember from our properties of cyclic quadrilaterals, angle ABC is supplementary to angle ADC, right? But since we also know that angle ABC is equal to angle AFE, this means that angle AFE is supplementary to angle ADE. So since angle ABC equals angle AFE and ABCD is cyclic, angle AFE and angle so these are supplementary. And since we know that these are supplementary from our conditions of proving a quadrilateral is cyclic, we know that ADEF is cyclic as well. And this is nice. So even though we have shown that ADEF is cyclic as well. And now we're going to use another condition that we haven't used yet. We're given that AB is equal to BC. which means that triangle ABC is isosceles. And since AC is perpendicular to BE, triangles let's call this point point P. We know that APB and BPC are right triangles. And in fact, they're congruent, simply because BP is a leg of the triangle, and given that BA is equal to BC, so by hypotenuse leg, triangle APB is congruent to angle CPB. Now this is nice as well, since now we know that AP is equal to CP, and since triangle AEP and CEP are right triangles as well, we know that triangle AEP is congruent to triangle CEP, simply because both of their legs are equal, right? I'll put that down as well. Since AP is equal to CP, know that they're congruent. Which is nice. So now we have more angle conditions. Okay. So now we'll use the fact that we have created a cyclic quadrilateral. So now we have two cyclic quadrilaterals, which is really nice. So we know that since ADCB is cyclic, angle ABD is congruent to angle ACD. Notice that they both cut off arc AD. However, we've also established that triangles AEP and CEP are congruent, which means that triangle EAC is isosceles, right? Because we have that EA is equal to EC, so because these two triangles are congruent. So this means since triangle EAC is isosceles, angle EAC and ECA must be congruent. So this angle is congruent to them as well. Now we focus on a cyclic quadrilateral ADEF. Okay. Notice that angle FDE and angle EAF both cut off arc FE, since it's cyclic, right? So based on a property of cyclic quadrilaterals, we know that these two angles are congruent. Okay, now let's look back at cyclic quadrilateral ADCB. Notice that angle BDC is equal to angle BAC, right? Because they both cut off arc BC. They both inscribed angles of arc BC. So, and also by a property of cyclic quadrilaterals, they are congruent. So we can draw that in. Let's use a different color. Yeah, should be good. These angles are congruent. However, at this point, notice that since we know that angle BAE and angle FDE are congruent, right? They both have these two lines across them. But angle FAC and angle EDP are congruent, which means that the it means that angles BAC minus angle BAE minus angle FAC, which is like this angle, which is angle CAE, must be equal to angle FDB, simply because they're both the angle with two lines subtracted by the red angle, right? However, angle CAE is the angle with the one line across it, so we can mark that as well. I don't know if it's working. So we know that angle FDB is equal to angle CAE, right? Mark them in blue, maybe. Why would we do that? Since we already know that this angle is already marked in with one line. Since we want to relate this angle with the other angles that we've already created, right? But now we'll notice that angle FBD is also the angle with one line across it, one dash. And also, since we've established that angle FDB is also the angle with one dash, right? Since this angle is equal to angle CAE. So this is what we wanted to show. We wanted to show that angle FBD was equal to angle FDB. And we already established that since, yeah. And now we're basically done. Since we've shown that angle FDB is equal to angle FBD, this shows that triangle FDB is isosceles. And since these base angles are congruent, FD equals FB. And this is what we're asked to prove, right? So now we're done. Since we've shown that FBD equals FDB, triangle FDB is isosceles. Hence, FB equals FD, and we're done. Okay, so that'll conclude the stream for today. If you have any questions, you can message them in the Discord server, and one of our staff will answer it. There will also be a problem set that'll be posted in our Discord server and on our website. There'll be plenty of exercises for you to try out. They'll be at many difficulty levels, so just try to do the problems that cater to your ability. Yeah. Also, feedback is greatly appreciated since this is our first stream. Yeah, thanks for the stream. Yeah, no problem. Yeah, that's it. Thank you. See ya. Bye.